Okay, so now we're going to talk about the normal vector. Again, we're trying to find a rotated version of ij and k, specific to each curve. Last time we already found the first candidate, which is, you can think as playing the role of I, which was a tangent vector. Which is nothing but the speed, the velocity divided by the speed of a curve, or of a particle representing the curve. Now, what we are going to do now next is work with the tangent vector in order to extract a new unit vector. One of the properties of the tangent vector, which I mentioned before, is that it's a unit vector, so its norm is 1. And this is something we had done before, but let me do it again because it's useful. If you square both sides, then that means that the norm square continues to be 1, but the norm square is just the dot product of the vector with itself. Okay? And so you can differentiate both sides of the equation with respect to time. Sorry, I'm getting ahead of myself. This is going to be 0, but not yet. So you get here 1, but now you apply the product rule to this. So you get the derivative of the tangent vector with respect to t dot t plus t dot the derivative of the tangent vector with respect to t equals 0. And so again, these two are really the same, so you get twice this dot product equals 0. Which means that dt okay, so that means that this vector, the derivative with respect to time of the tangent vector, is orthogonal or perpendicular to the tangent vector. Now, again, like the tangent vector is morally like the velocity, more or less. So this is a bit different because we had to rescale it. But so if you ignore the difference, the derivative of the tangent vector is almost like the derivative of the velocity, which is almost like the acceleration. So that means that this vector could be interesting. It could be related to the acceleration of a particle, which will be the case. But so what this means is that we should maybe study this vector, but again, there will be an issue, which is that this vector may not necessarily have unit norm. Another issue is that, again, the units of this vector are 1 over time, or what's known like 1 over seconds, which is like hertz or frequency, just because t was without units, and when you take a derivative, you're sort of getting the units of the denominator, and so the denominator has units of time in quotes. It's not really like a denominator, but at least for unit purposes, it works like that. So this has units of 1 over t. And again, we don't want to work with something that has units. And so what we do, so we have the same two issues that we had before with the velocity vector, that it had units and it didn't have unit norm. So we do the same solution, we apply the same approach, which is just rescale it. And so the definition of the normal vector is just it will be the derivative of the tangent vector, which is really the vector we care about, but now you have to rescale it. Okay, so let's do an example to see how this looks like. Okay, now let's find the normal vector of the following trajectory So the velocity is 0, 1, 2t. The speed is square root of 1 plus 4t squared. Okay. The tangent vector is velocity over speed. That gives you 0, 1 over 1 plus 4 t squared, 2t over root of 1 plus 4 t squared. And then, for the normal vector, we need the derivative of this tangent vector. Now, you could move this to the numerator. It's an option, but you could also apply the quotient rule, whatever you prefer. So the first derivative will be 0. If you apply the quotient rule here, it will be the derivative of the first one, which is just 0, times the second one, minus the first one times the derivative of the denominator. So this becomes 1/2. Okay. Over the denominator squared, which is 1 plus 4t squared. Okay. And then if you do the same for the last entry, you get by the quotient rule, you get the derivative of the first one, which is 2, times the second one, minus the first one times the derivative of the second one, which is 1/2, again, times 1 plus 4 t squared to the negative 1/2 times, I forgot, when we took derivatives here, I had to multiply by the chain rule. So I need to multiply by 8t. Sorry about that. Okay. And so, let's see, what's the best way to do this? Notice that there's going to be a 1 plus 4t squared in the denominator everywhere. So I might as well factorize it. I guess there's nothing much to do. And then this becomes minus 4t over square root of 1 plus 4t squared. And then this becomes 2 root of 1 plus 4t squared minus what? So minus 8t squared. Yes, 8t squared over root of 1 plus 4t squared. And let's do one final simplification before computing the normal vector. So you can just say this is 1 over, I can factorize the square root, and then this becomes 3/2, and so 0 minus 4t, and I use common denominator here, so this becomes 2. Okay, yes, it's not too bad. Oh, yeah. So basically what happened, maybe I should do an extra step here. I use common denominator, so this becomes this thing. And so usually when you distribute, you get 8t squared, which cancels this 8t squared, so you just get 2 over this, but then you factorize it again. So hopefully this will be the right thing. This is the derivative, and then you compute the norm of this derivative of this vector. And that will just be 4 plus 16t squared over 1 plus 4t squared to the 3/2. Okay? There's not too much you can do here to simplify. You could factorize a 4 upstairs. Oh, yes, good. So if you factorize a 4 upstairs, you get 1 plus 4t squared, root of that, and so you got a 2 here, and you get good. Oh, this is not too bad. And so that means that in this particular case, the normal vector is this green vector, which is divided by this expression, which gives you and this gives you 1 over root of 1 plus 4t squared, 0 minus 2t1. So this should be the normal vector. And you can check at least that it does have unit norm. And you should also check that it is perpendicular to the tangent vector. So that, like the velocity vector was 0, 1, 2t, I think. Yeah, you can check that it will be perpendicular to the tangent vector, which means that I didn't screw it up completely. So next video we'll talk about how this normal vector is related to the acceleration.